We have seen in our previous lecture that atmospheric pressure is equal to 101,325 pascals. Now it is quite a significant amount. But where do you think this figure is actually coming from? Or in other words, how do you think is the atmospheric pressure calculated? The atmospheric pressure was first calculated by a scientist who was known as Evangelista Torricelli. Evangelista Torricelli used a particular instrument for measuring the atmospheric pressure. This instrument that Evangelista Torricelli used was invented by him only. This instrument is known as the barometer, and with the help of barometer he was able to calculate the atmospheric pressure. So let us find out what a simple barometer looks like, and with the help of it how we can calculate atmospheric pressure. So this is what a simple barometer looks like. It consists of a long thin tube. Now this tube is closed at one end and open at the other, and it is 100 centimeters or 1 meter long. Now initially this tube is filled with pure mercury in such a way till the brim, so that no air bubbles exist inside the tube. After filling it, the open end is closed with the thumb and inverted into a trough of pure mercury. Now while inverting it, care should be taken that no air bubbles escape and move into the tube. Now once the tube has been inverted and kept in the trough of mercury, it will be noticed that the level of mercury in the tube falls to a certain extent. If we measure the height from the surface of mercury in the trough till the point where the liquid has fallen in the tube, that particular height or length will be equal to 76 centimeters. So let us find out why in the first place liquid is flowing out, that is mercury is flowing out from the tube and into the trough. Over here we consider both the initial and the final condition. This is the initial condition and this is the final condition. Now in the initial condition, if you notice, the liquid, that is mercury, is completely full in the tube, and in this manner it has been inverted into a trough of mercury. So if you now observe closely, the pressure that is acting on the trough of mercury, that is on the outside on the surface, is the atmospheric pressure. Now initially while performing the experiment, that is absolutely at the beginning, I had mentioned that mercury should be filled in the tube in such a way so that no air exists inside the tube. So what does this mean? This means that inside mercury there is absolutely no air. So as a result, what happens? At this particular point, which is inside the tube, atmospheric pressure is not acting. Instead, pressure due to mercury is acting at this point. So let me call this, so this point, let us consider A, and the point outside C. So now we found that liquid is flowing from inside to the outside. So what does this mean? This means that pressure must be greater inside the liquid as compared to the outside. If we compare these 2 points now, that is point A and point C, we will find that the pressure of the liquid column, that is 76 centimeters in height, from point B is acting at point A, and at point C atmospheric pressure is acting. Obviously when liquid is flowing out from the tube and into the trough of mercury, there is a change in level of mercury in the trough and a change in level of mercury in the tube. So now let us find out why liquid flow is stopping. So initially mercury flowed from the tube to the container, that is from the tube into the trough, and we have studied earlier that liquid always flows from one region to another region only when there is a pressure difference in between those two regions. So since liquids or fluids for that matter flows from a region of high pressure to a region of low pressure, what can we say? We can say that initially pressure inside the tube was higher than pressure outside. Or in other words, we can say that initially pressure inside the tube was higher, that is pressure due to mercury, than pressure due to the atmosphere. Now when the liquid stops moving and becomes stationary at point B, that is the time when there is no more pressure difference in between C and A. Now at point C, atmospheric pressure is acting because point C lies on the trough of mercury. However, at point A, there is no atmospheric pressure. Instead, the pressure acting at point A is only due to the liquid column or the mercury column AB, which is 76 centimeters in length. So what can we say? We can say that this pressure being exerted by the mercury column will be equal to the atmospheric pressure that is acting on the surface of mercury in the trough. So as you can see from this equation, pressure exerted by mercury column, that is this, at this point will be equal to the atmospheric pressure. So now let us find out how we can calculate the atmospheric pressure with the help of this information that we obtained. So this height, that is 76 centimeters from A to B, has a particular name. This height is known as the barometric height. The vertical height of the mercury column from the mercury surface, that is the trough level, to the point where it becomes stationary is 76 centimeters, and this is known as the barometric height. And it is this barometric height which we will be using in our calculations for atmospheric pressure. So consider this scenario where the barometer, the simple mercury tube barometer, is taken to 2228 meters above sea level. What happens in that case? Since we are moving up or the altitude is increasing, the atmospheric pressure will decrease. So as a result, when atmospheric pressure is decreasing, it means that pressure inside the tube is greater than pressure outside. As a result, more mercury will flow out from the tube and into the trough. The reverse happens if we go down below sea level. Now in this picture, we find that the Dead Sea has been shown. The Dead Sea is a sea on Earth which is actually 429 meters below sea level. Quite interesting, isn't it? That a sea actually exists below sea level. So if one were to go to the Dead Sea with a mercury tube barometer, the pressure exerted on the trough, on the surface of the mercury in the trough, would be more as compared to the pressure inside the tube. So as a result, what happens? Mercury will flow from high pressure to low pressure. And since the altitude has decreased, we have gone below the sea level, and pressure has increased on the trough, liquid, that is mercury, flows into the tube from the trough. So this is how the level of mercury in the tube changes as we go up or down as compared to sea level. So now let us find out how we can calculate the pressure that is being exerted by 76 centimeters of mercury column. Earlier we found out that this pressure being exerted by 76 centimeters of mercury column is equal to atmospheric pressure, because when the mercury becomes stationary at point B is at a height of 76 centimeters from the surface of mercury in the trough, and this is exactly equal to the atmospheric pressure. That is, the pressure exerted by the mercury column will be equal to the atmospheric pressure. So if we can find out the pressure exerted by mercury column, we can find out the atmospheric pressure. So earlier we had found what is the pressure exerted by a liquid column of density rho and height from top h. So over here we write the density of mercury as rho, the height of mercury column from the top as h, and acceleration due to gravity as g. Now the density of mercury is 13,600 kgs per meter cube. The height of mercury column is 76 centimeters. So converting it into SI unit, it will be 0.76 meters. And the acceleration due to gravity is 10 meters per second square. So thus, we have this equation as I showed you. Now over here, for more accurate calculation, the acceleration due to gravity is not taken as 10 meters per second square. Instead, its actual value, that is 9.8 meters per second square. So once this calculation is done, what is the result we are obtaining? Firstly, we find that 2 meters over here are getting cancelled and 1 unit meter remains. So the resulting unit that we get will be kg per meter per second square. And the quantity that we get is 101,325 pascals, or 101,325 kilograms per meter per second square. Does this value seem familiar to you? That's right. This value is nothing but the pressure that is exerted by the atmosphere, which in turn is equal to the pressure exerted by 76 centimeters of mercury column. Thus, with the help of a mercury tube barometer, we were able to calculate the pressure exerted by the atmosphere, which is equal to 101,325 pascal, or 101,325 pascals. So since the atmospheric pressure is 101,325 pascals, we can also say that this pressure is equal to the pressure exerted by 76 centimeters of mercury column at sea level, or we can also say that it is equal to pressure exerted by 760 millimeters of mercury column at sea level. It's nothing but converting centimeters to millimeters by multiplying 10. Now with the help of this barometer, we can actually use it to forecast the weather. Weather forecast to an extent is quite possible with the help of a barometer. Let us find out how. So when there is an increase in temperature of air, the kinetic energy of the air molecules will increase. Why? Because the kinetic energy of molecules is directly dependent on the temperature of the medium. So due to this, they start to vibrate more vigorously with a greater speed, because kinetic energy is directly influenced by the speed of the molecules. So it is due to this reason that air expands due to an increase in its temperature. As a result, what happens is the volume increases, but however, the mass of air does not change. So density, that is equal to mass by volume, since mass is not changing but the volume is increasing, the density is decreasing, and thus since density is decreasing, we can say that the atmospheric pressure also decreases. Why? Because the height from where we are considering the air column is not changing. We are considering a particular height from the top, that is the altitude remains constant. Acceleration due to gravity is also not changing, but density of air is decreasing, and due to that reason the atmospheric pressure is decreasing. Conversely, if there is a decrease in temperature of the air due to contraction of air, the atmospheric pressure will increase. Now let's see what happens if there is an increase in humidity or the moisture content of air. Now when there is an increase in the moisture content of air, that is when water vapor amount is increasing, it means that per unit volume there is more water vapor as compared to oxygen and nitrogen. And water vapor happens to be a relatively light gas. So what happens? When water vapor content per unit volume is becoming more as compared to oxygen and nitrogen, the mass is decreasing. So if we consider a fixed volume, and if mass decreases, then density will decrease. So since density is decreasing, in the equation P equals to rho into H into G, H and G remains the same, but rho is decreasing, and thus the atmospheric pressure PATM will decrease. The converse is also true, that if there is a decrease in moisture in the air, or if there is a decrease in humidity, the atmospheric pressure will increase, because then per unit volume there will be less amount of water vapor and more amount of oxygen and nitrogen. So thus, let's see what happens when temperature increases. We found out that when there is an increase in temperature, the barometric height will fall. Now, due to this increase in temperature, the barometric height fall will be a sudden one, due to which the pressure will also fall suddenly. So, if there is a sudden fall of barometric height, it indicates that there has been a sudden fall of atmospheric pressure, and it usually indicates the onset of a cyclone. On the other hand, if there is a gradual increase in moisture, it will mean that the barometric height will gradually fall. It will not be a sudden fall. This indicates that the atmospheric pressure has also fallen gradually, and this indicates a possibility of rainfall. As you might be knowing that an increased quantity of moisture in the air means possibility of rainfall, and this is how the barometric height is helping us predict it. The converse is also true. Let's say the moisture content in air is decreasing. So due to this decrease in moisture content, if it is gradual, then the barometric height will gradually increase, which will signify an increase in pressure. So it means that dry weather is about to come on, or the onset of dry weather is at hand. On the other hand, if there is a sudden decrease in moisture content of the air, it will mean that the barometric height will rise suddenly, which in turn means that the pressure of the atmosphere will have undergone a sudden increase. This means that extremely dry weather is about to be coming on in the next few days. However, if there is no abrupt change in the barometric height, that is, if the height of the mercury column in the tube remains the same, then it means that normal weather conditions will be encountered in the next few days. Or in other words, there will not be any heavy rain or cyclonic weather or even dry or extremely dry weather. Normal weather conditions that had been prevailing so far will be there for the coming few days. And this is how we can use barometric height in order to predict weather conditions. So taking a quick recap, we studied about the barometer. The barometer is an instrument that was first invented by Evangelista Torricelli, which he used to measure atmospheric pressure. We found the same, that is how we can use the barometer in order to measure atmospheric pressure. Atmospheric pressure is equal to the pressure exerted by the liquid column, that is the mercury column, when its height from the trough to the point where it becomes stationary is 76 centimeters. Under such a circumstance, no mercury is flowing into or out from the tube. And this is why the atmospheric pressure and the mercury pressure inside the tube is equal. And this is how we found out the value of atmospheric pressure. That is from the value of pressure exerted by the mercury column. And we also found out how we can use the barometer and the barometric height in order to predict changes in weather.